Sydney, do you want to get started?
Yeah, I was thinking, oops, can you hear
There's
me?
another person. Yes, I can hear you.
Okay, for some reason it looked like it was muted on my end. Yeah, I think we can get started, or at least I should make sure that my technology works out. Let's see if we can do better than last year. So far, so good. Hey. Alrighty, well, I think we can go ahead and get started. It's a couple minutes after 11. Welcome to our very first day of the Organic Chemistry Summer Program. My name is Sydney, and I wasn't at orientation yesterday, but I'm one of the people who's going to be giving lectures this summer, and I'm super excited that you guys have all signed up to be a part of this program, and let's get started. Alrighty, so day one, just to recap, as I'm sure you heard from orientation, we've got lectures Monday, Wednesday, Friday, all at 11 a.m. Eastern time or Eastern Standard Time. Study groups start this week. Check with your study group leaders to make sure that you have all the right dates, times, and Zoom links for those. And our first exam is going to be this Friday. More information about that will be forthcoming as well. So today for lecture, we're going to recap some organic chemistry related Gen Chem. Specifically, we're going to review hybridization, formal charge, and resonance. Then we're going to introduce how we draw structures in organic chemistry. Now, I know you guys might have questions, so we're going to give you lots of opportunities to participate and to speak out. Alrighty. So the first hybridization scheme that we're going to review is SP hybridization. And I know in Chem 2070, we referred to hybridization schemes as SP plus P plus P or SP2 plus P. Well, when I started doing organic chemistry, a huge surprise for me was that we literally just call it SP hybridization and leave this out. But I left the plus P in the parentheses because that was confusing for me, and I want everyone to know that it's the same thing. Anyhow, molecules with sp hybridization have a steric number of 2 or a steric number of 6. And what that means is that the central atom has 2 or 6 groups around it. And when I say a group, I mean either a bond or a lone pair. Now, this hybridization includes 2 sp hybrids and 2 p orbitals. So if you look down here, I have drawn out 2 sp hybrids and 2 p orbitals. And if I were to kind of combine those up, as I'm sure you might remember from general chemistry, you've got your sp hybrids kind of like that. I'm going to draw one vertical p orbital like this. And I'm going to draw another p orbital sort of going in and out of the plane of the board, which is represented by this front circle and this backward circle. So this is what an sp hybridization looks like with all of the orbitals added together. Now, the molecular geometry for sp hybridization is linear if there are 2 bonds, and the bond angle is 180 degrees if you have 2 bonds. As you might remember from Chem 2070, lone pairs take more space than bonds. So the bond angle is going to be decreased if you had a bond in a lone pair versus 2 bonds. The next hybridization scheme to review is sp2 plus p, or in orgo speak, just sp2. Now, molecules that have sp2 hybridization have a steric number of 3 or 5, meaning that the central atom has 3 or 5 groups around it. And to make sp2 hybridization, you're going to have 3 different sp2 hybrids, and you're also going to have a single p orbital. And those are going to be organized kind of like this. you've got your hybrids kind of arranged like that. And then you have your p orbital, which is going in and out of the plane of the board, again, as represented by the sort of two concentric circles, like so. And then the molecular geometry for an sp2 hybridized molecule is trigonal planar if there are 3 bonds, and the bond angle is going to be 120 degrees if you have 3 bonds. And then before I move on to the next hybridization scheme, oh, I see that Ashley has already beat me to it. Feel free to ask questions in the chat. Alrighty, last hybridization scheme is sp3 hybridization, and molecules that are sp3 hybridized have a steric number of 4, meaning the central atom has 4 groups around it. And if you look at the composition of an sp3 hybridized atom, you will see that it just has the 4 sp3 hybrids arranged sort of in a tetrahedron. So it looks kind of like that. And again, as you might expect, the molecular geometry is tetrahedral if there are 4 bonds. And the bond angle, if you have 4 bonds, is 109.5 degrees. Now, before we move forward and do a little bit of practice, are there any questions pertaining to hybridization? Alrighty, it seems pretty quiet, so I'm going to assume that you guys understand what's going on. And now we have an opportunity where we can kind of practice what we have just covered or just reviewed. And I would love it if you guys would be willing to participate by either unmuting yourselves or typing in the chat as we review the hybridization schemes for the following molecules. So let's start with the H2O molecule up here in the top left corner. Does anybody know what the hybridization scheme for H2O is?
Would it be SP?
Well, for H2O, we can first start by counting the groups that we have around the molecule. So if I can get my highlighter to work, we have 2 lone pairs up here. So those are our first 2 groups. And then we have 2 hydrogens down here. So those are our next 2 groups. And then, so 2 plus 2, that equals 4. And we have 4 groups around our oxygen, which is the central atom. Given the fact that we have 4 groups, does anyone know now what the hybridization for the molecule is?
Wouldn't it be sp3?
Yes, thank you. Oxygen is sp3. Alrighty, let's move on to our next molecule down here. Would anybody like to take a stab at the hybridization for, I think, this amide?
Is it sp3?
Yeah, exactly. We have 4 groups around our nitrogen, the lone pair, and the 3 bonds. So this is sp3 hybridized. And for anyone wondering, there's supposed to be CH3s on this molecule. So it's a nitrogen with a lone pair and 3 different CH3 groups, or 3 different methyl groups. And you'll learn more about how we classify orthomolecules later on in the lecture. Alrighty, moving on. We've got this xenon difluoride. What is the hybridization of xenon difluoride?
Is it SP2?
Yes, it is sp2. Thank you, Precious. So we can see that there are 5 groups around our xenon. this question is a little bit tricky because these lone pairs are notated using wedge dash formation. So hopefully that didn't trip anybody up. And if we have 5 groups, that is sp2 hybridization. Awesome. Now, moving up to this molecule, which you might have seen on some of the 2070 practice exams. I know I definitely have. What is the hybridization of this molecule? Well, maybe it would help if I showed, well, not showed, but like shaded that this carbon is our central atom. So how many groups do we have around the carbon?
Is it SP3? Is there like 4 groups?
4 groups. I see where you're coming from, but actually there are 2 different groups around the carbon. We have 2 other carbons. Does that make sense? Because we've got a double bond between our central carbon and the carbon on the left, and we have a double bond between our central carbon and the carbon on the right. So does that make sense?
So basically, double bonds and single bonds are kind of the same.
Well, when we're looking to count the number of groups, yes, there definitely are a lot of differences between the structure of like single bonds and double bonds. But when we're thinking about like how many groups are there, we could like assume, okay, any type of bond, we're just looking at like how many things the central atom is connected to. If this were a triple bond, we could assume still, well, not still assume, there would be still 2 different groups connected to the carbon, regardless of what type of bonds these were. Does that answer your question?
Yeah, thank you.
I see we have a raised hand. Sydney, do you want to go ahead?
Yeah, so I was wondering, because in this case our like the carbon in the middle is our central atom, when we're counting up those bonds, we don't count anything that's like not directly connected to that. So like the other 2 hydrogen bonds with the other C's wouldn't count in this.
Yes, and I can see how perhaps the wording of this prompt might have been a little bit confusing. To be more specific, we're looking for the hybridization of the central atom. And I'm sure you might remember from 2070 where they had problems where they would say, what's the hybridization? And they would put like the little line next to the atom that they wanted the hybridization of, like what they wanted you to consider the central atom as. So I can see how if we just gave you this problem on a test and didn't say anything, that would be confusing. But for, as you'll see in study group, like we're more specific about what we want you to consider the central atom as, because obviously if we had a line next to this carbon on the left or this carbon on the right, your answer might be different. But we're considering this carbon right smack dab in the middle to be the central atom.
Thank you.
So we have 2 groups around the carbon we are considering as the central atom. 2 groups. So based on that, what is the hybridization for this carbon here?
SP.
Yup. This carbon is sp hybridized. Alrighty. Moving on to our next molecule, this is SF6. And I think it's a little bit more obvious in this case, as is most of the cases, but we're considering the sulfur to be, the central atom. So I guess I'll go ahead and highlight that. Does anybody want to go ahead and take a stab at what the hybridization for the sulfur is?
Wouldn't it be SP?
Yep. So if it has 2 groups or 6 groups around it, the central atom will be sp hybridized. So kind of just like this example. Alrighty, last molecule. We have our HCN, and we are going to be considering this carbon as the central atom. So looking at that, what is the hybridization for the carbon?
SP.
Yep, very good, thank you. We have two groups around our carbon. The two groups are this nitrogen and this hydrogen. And I guess that kind of goes along with what I was saying earlier. The carbon is connected to the nitrogen by a triple bond, and this carbon is connected to the hydrogen by a single bond. But regardless of what type of bond we have, we still have two different groups around our carbon. So it's sp hybridized. Alrighty, so before we switch gears a little bit, are there any questions? Alrighty, let's move on and talk a little bit about formal charge. There are some easy steps that you can use to calculate formal charge. The method that I like to use is to first consider how many electrons the atom should have around it. And you can find this out by looking at that atom on the periodic table, and you look at the number above that atom on, you look at the number above the column for that atom on the periodic table. That's an easy way if you just need to refresh yourself. That's the amount of electrons the central atom should have around it, or the amount it wants to have around it to be stable. Next, you can consider how many electrons the central atom, or whichever atom you're looking at, does have around it. So you do that simply by looking at the example problem. And then the formal charge on that atom is equal to the number of electrons the atom should have minus the number of electrons it does have. And then just something to keep in mind is that when you're finding the formal charge of a molecule overall, you're going to want to add up the individual formal charges for each atom. So to make this all make sense, let's go ahead and quickly do a practice problem. Let's take a look at this molecule right over here. We've got sulfur connected to two oxygens and a methyl group, a CH3. So let's start with the formal charge for the atom in the middle, which is the sulfur. So if you were to look at your periodic table, you would see that sulfur and oxygen are both in the same column, and they both want to have 6 electrons around them. So I'm going to draw a W that stands for the amount of electrons sulfur wants to have, and I'm going to write 6E because sulfur wants to have 6 electrons. And now I'm going to look at this molecule and figure out how many electrons the sulfur does have around it. Now here is where things start to get a little tricky, because it's kind of easy to see, okay, we have a lone pair. The sulfur clearly has at least 2 electrons around it, but we have 3 bonds. So for bonds, when we're calculating formal charge, each bond gives 1 electron to the sulfur. So in this case, we see that sulfur has 2 electrons from the lone pair, and then 3, 4, 5 total electrons because it has 3 bonds. What I like to imagine is, suppose we cut these bonds in half, since single bonds have 2 electrons, and we think of giving 1 electron to the sulfur and 1 electron to whatever other atom, the oxygen or the carbon in this case, is connected through the bond. So thereby, sulfur has 5 electrons around it. Now, based on the amount of electrons that sulfur wants to have and the amount of electrons that it does have, Does anybody want to shout out what the formal charge on our sulfur is?
+1.
Yep, thank you so much. So basically, what we do to get +1 is we subtract 5 from 6. I'm going to try and write it in here. 6 minus 5 equals +1. So that's the charge that's going to be on our sulfur. Next, we have 2 oxygens. So does anybody want to go ahead and say how many electrons the oxygens do have around them? Because we know that they both want to have 6 electrons, just like sulfur did.
7.
Yep. Both of these oxygens have 7 electrons around them, and that's because we have our 3 lone pairs, 1, 2, 3, 4, 5, 6. And then we've got a bond between oxygen and sulfur, which gives oxygen 1 additional electron. So oxygen has 7 electrons around it. And based on that, what's going to be the formal charge for our oxygens?
-1.
Thank you, Amy. Yes. So both of these oxygens are going to be negatively charged. -1, -1. So we have the formal charges for our oxygens and for our sulfur. What is the overall formal charge for this molecule?
-1.
Exactly. Thank you so much. So again, what we do is to get the overall formal charge for the molecule, we add up the individual formal charges for the oxygens and for the sulfur. And if we were to add -1 plus -1 plus +1, we'd be left with just -1. So that's the formal charge for this molecule as a whole. Are there any questions about how we did this problem?
How did you get the sulfur charge of +1?
Okay, so for the sulfur, what we did is we saw that sulfur wants to have 6 electrons around it. And then we counted up that the sulfur did have 5 electrons around it because it gets 3 electrons from these 3 bonds. And it also gets 2 electrons from the lone pair. So 3 plus 2 equals 5. And then our formula for calculating formal charge is subtracting the amount of electrons the atom should have minus the electrons it does have. So that would be 6 minus 5, which equals +1. Does that make sense?
Yeah, thank you.
Alrighty. So
Um,
I think we're
yeah.
going to,
Sorry, do you just forget the CH3 group when calculating it? Like, why do we ignore it?
great question. So for whenever you see a CH3, I'll tell you why you can ignore the rest. Well, not ignore the rest, but ignore the CH3 for calculating formal charge. So yeah, this is showing. I just went ahead and drew up basically what this molecule is. Another orgo shorthand is to draw an R in terms for rest of the molecule. So basically this R represents the sulfur and these 2 oxygens. So we have our CH3 and our R. We know that whenever we see, we know that carbon wants to have how many electrons around it?
4.
Thank you. So carbon wants to have 4. Whenever carbon is bound to 4 different atoms, how many electrons does it have around it?
Also 4?
Exactly. And then if carbon wants to have 4 electrons bound around it, and it does have 4 electrons around it, then what is the formal charge on carbon?
0.
Exactly. So that is why whenever you see a CH3 connected to another atom in a molecule, you can always just ignore that because carbon bound to 4 different things, that means that it has a formal charge of 0. Does that answer your question?
Yeah, thank you so much.
No problem. 4 minus 4. Perfect. Alrighty, are there any other questions before we move on? We can definitely do more examples at the end of lecture.
I also have a quick question, but it's regarding the triple bond, like in the first molecule on the slide.
Okay,
So like if you were dividing the bonds there, how would you do that when you like think about the formal charge?
you would actually do it the same way we did our single bonds. I would literally just chop that in 3, and I would say that for carbon, carbon has, also there's supposed to be a CH3 over here. I think it might have gotten cut off. I would say that this carbon has 1, 2, 3, 4 electrons around it. So that carbon is pretty happy because, as we just discussed, carbon wants to have 4 electrons. And I would say that this nitrogen over here has 1, 2, 3, 4 electrons around it as well. Because just as we divide a single bond in half and say that each bond gives 1 electron to the nitrogen, we divide a triple bond in half and say, okay, instead of just 1 electron, the nitrogen is now getting 1, 2, 3, 4 electrons. So nitrogen also has the same number of electrons around it as carbon. Did that answer your question?
Yeah, thank you.
Perfect. Alrighty. Let's move along a little bit and talk about resonance, which is going to become a big part of your life for the next year. So resonance is used to show the localization of the localization of electrons on different atoms in a molecule. So one of my favorite professors from Cornell, the late Dr. Rutledge, described resonance as a game of hot potato. So imagine if we put, excuse me for a moment, imagine if we put all the OCSP students in a giant circle and we gave you all this extremely hot stone to hold. And if you hold it for too long, you're going to burn your hands. But if you pass it to your neighbor super quickly, you can not burn your hands as much. That's kind of the idea behind resonance. A lot of times, especially when atoms have a positive charge or a negative charge, that deficiency or surplus of electrons can be really unstable for a molecule. And in organic chemistry, molecules also always want to be as stable as possible. So they can get rid of that surplus or deficiency of electrons by passing the charge around from atom to atom to atom. And it's important to note that you can also have resonance even if your molecule is completely neutral. But when you draw resonance structures, when you draw resonance structures, your structures will always have the same charge from one structure to another. So if you started with a neutral molecule, you're only going to have resonance structures that are passing electrons around that have that neutral charge. Same with a positively charged molecule, you're only going to have resonance structures that are positively charged, or a negative resonance structure, a negative molecule, you would only have negative resonance structures. Got to keep the charge constant. So resonance can occur whenever you have a double or triple bond next to an electron that's electronegative, negatively charged, or positively charged. And this electronegative example is a good case of a neutral molecule that has some resonance structures. So let's go ahead and look at what the resonance structures for these will look like. So first up, we have our electronegative molecule. We can see that we have our double bond right here. As you might remember from Chem 2070, oxygen is pretty electronegative. and we have a nice lone pair on our nitrogen. So I'm going to go ahead and draw out this molecule again so we can have our next resonance structure. And then we use curved arrows in organic chemistry to show the movement of electrons during resonance structures. So what I'm going to do here is I'm going to draw a curved arrow going from the lone pair that is on this nitrogen, and I'm going to draw the creation of a double bond between the nitrogen and this carbon. Now, let me see if I can represent that clearly here. We have a carbon, we've got our new double bond, and we've got our single bond from this carbon to this methyl group. Now, a problem is that carbon follows the octet rule. In fact, we're going to discuss in a moment that most atoms follow the octet rule. So we can't maintain our double bond from the original structure. And for that reason, we're going to create a single bond instead between carbon and oxygen. I'm going to show the electrons from that double bond localizing on the oxygen to create a lone pair. And we have a negatively charged oxygen and a positively charged nitrogen. So that's our resonance for an electronegative molecule. And as you can see, the original molecule is neutral. If we add up the formal charges for the oxygen and the nitrogen, we still have a final resonance structure that is also neutral. So charge was maintained. Let's look at a negatively charged example this time. And here, we're going to try and be pushing this negative charge away from this oxygen and over to another atom in the molecule. So what we can do, I'm going to use my curved arrows again. I'm going to show one of these electrons from the oxygen, well, from the oxygen that's on the bottom right, going to create a double bond between the carbon and this oxygen. And again, we're going to have a problem that carbon can't have more than 4 bonds. So we're going to have to use some of the electrons in this double bond and localize them on the top oxygen. Therefore, carbon is able to follow the octet rule. This oxygen up here gets an extra lone pair and a negative charge, and we maintain our negatively charged molecule. We started with a negative charge, we ended with a negative charge at our last resonance structure. And lastly, let's do a positive resonance structure. So this kind of is the same idea as a negatively charged resonance structure in that we are trying to relieve a deficiency of electrons. Let me go ahead and draw it out. As we can see here, this carbon has a positive charge. It only has 3 bonds. So what we can do is we can show the electrons from this bond, this double bond, localizing to create a double bond between this carbon and this carbon. So I'm going to use my curved arrow again to show the movement of electrons. The head always starts at the source of the electrons and ends at where they're going to go. And we create a double bond that's instead between the carbon on the left and the central carbon. And now we have a new carbocation, which is a positively charged carbon. Now the positive charge is on the carbon that's on the right, instead of the carbon that's on the left. So once again, as has been the case with our electronegative and negatively charged example, we've maintained the charge for the molecule. It was positively charged here, and it's positively charged at the end, or in our resonance structure as well. Now, before I pass it over to Samantha, Are there any questions? Alrighty.
Awesome. Thank you, Sydney. Let me see if this works. Can everyone see this? Very
Yep, looks
happy that
good.
is hopefully cooperating today. Awesome. So I'm Samantha. I'm one of your other lecturers. Sydney and I will be doing it Mondays with you guys. So look forward to that. I'm just going to be going over a little bit more resonance. So like Sydney talked about, some of the major rules for resonance are going to be don't break single bonds or move bonds around. I added the caveat to connect different atoms because, of course, if we're moving bonds to connect different atoms, we're creating a new molecule that is not a resonance structure. Second is going to be don't exceed the octet rule for your second row elements. And so I'm going to go back for this first rule and look at one of Sydney's examples that she just went over. So you're going to see I drew it a little bit different, but it is the same molecule. So remember that our major resonance structure for this guy ended up looking something a little like this. And so using the curved arrow formalism, take the double bond, put those electrons on the carbon, and then put them on the single bond. And just so you guys are all clear on how that happened, I'm just going to go over that real quick. So remember, we start off with this molecule. Ooh, that is a little ugly. It's okay, you guys know. So you take one of the bonds from that double bond, pop it over on the carbon. Remember, there are how many electrons in one of those bonds? Anyone want to shout it out? Hopefully you're saying in the chat that it's 2. So we got these 2 electrons on that carbon now. Remember that this CH2 group is now a plus charge because instead of having those 4 electrons from that double bond, there's only 2. So 2 and then the 2 hydrogens is going to give you a plus charge. So now on this carbon, he's got 2, 4, 6, 8 electrons. And he is going to be, am I crazy? No, we are good. Negatively charged. And so remember that this is actually going to be a second resonance structure. It is not really a major contributor, but you're going to notice that the formal charge should add up to +1. So +1, -1, +1, same formal charge. Awesome. Let's finally get to that last resonance structure. Did not give myself much room, so I'm going to put him down here. So remember, we're going to use the curved arrow formalism again. We're going to see that we had this lone pair. Let's pop that lone pair back onto the single bond with the leftmost CH2. And that is going to get us what we had originally. So we get the second major resonance structure that Sydney went over before. Awesome. And so another way to think about don't break single bonds or move bonds is to say, essentially, look for double or triple bonds. So you're going to notice here, and in some of Sydney's examples, we looked at this double bond, we said, okay, we can liberate a couple of those electrons, move them around to the different parts of the molecule. Awesome. And so something else we are going to go over very soon is what's called separation of charge. So you're going to notice that, for example, in these 2 resonance structures, there's only 1 plus charge, right? Only 1 charge overall for a charge of +1. This resonance structure, still overall +1, but there are actually 3 charges here. And so we call this separation of charge. And generally, that is going to be pretty unfavorable for the stability of a resonance structure, and we'll talk about that in a moment. So second rule, don't exceed the octet for second row elements. So like Sydney was talking about, in general, you don't want to be breaking the octet rule. The only real exception to this that we're going to see a lot is sulfur, because it's hypervalent. Even then, you're not going to see sulfur too much. Most professors will go over it with you. So let's look at this example and see it's a little bit different, not the same molecule. Again, we have these 1, 2, 3 charges. So that is once again, separation of charge. And so let's go ahead and try to make a resonance structure for this guy. We're going to see, okay, we can either look for double or triple bonds, or we can see that carbon has an extra pair of electrons. So let's go ahead and move this over, get rid of the plus charge on the CH2. What's that going to look like? I'm just drawing out the hydrogens here. It's same difference. Awesome. Hopefully this will help you visualize it a little. So note now that we've moved that lone pair over to the left, this is now a double bond. Now that the CH2 has 1, 2, 3, 4 different pairs of electrons, its octet's going to be full, no more plus charge. So that carbon is happy, this carbon is happy, this nitrogen is actually still plus. And so we might be thinking, okay, well, we got rid of this plus charge, this minus charge. What if instead we had moved that lone pair over to get rid of that plus charge on the nitrogen? Let's try that. So arrow there, arrow back over there. So double bond on that nitrogen now. And what do you guys think about this structure? Does this look okay? Does anything look wrong here? Feel free to shout out if you see anything. All right, hopefully you guys have had a second to think about it. So let's look at this nitrogen. We have 1, 2, 3, 4, 5 lines, which means how many different electrons? That's going to be 10 electrons. And so is this breaking the octet rule? Yes, octet rule to add. So this is actually not going to be a resonance structure. Does that make sense to everyone? Cool. So now we are going to be doing a little bit more resonance practice. So do the following structures have resonance? We're going to see this first guy is benzene. He's going to be your friend in orgo. And so once again, we're going to see, okay, double bonds. What can we do with that? So one thing you can do is move every single double bond over by 1. You can go clockwise, counterclockwise. Does not really matter. I'm going to go ahead and draw this out real quick. This will take me a minute. That's very ugly. It's okay. That's not even 6. Never mind. There we go. That looks slightly better. And you're going to notice that that took me a while to draw out, right? And it's probably taking you guys a while if you're drawing it too. And so very soon we will be going over the way we draw different organic molecules, and you will see that this will become a lot easier. And so you're going to notice here that this kind of looks like the same. You might be like, okay, what changed here? Remember that all these double bonds moved over one. So we do consider this a different resonance structure because, for example, maybe if we had labeled our carbons 1, 2, 3, 4, 5, 6, and did it over here as well, that these double bonds did move, even if this looks functionally the same. And so sometimes you're going to see benzene drawn as this, with the circle in the middle, hexagon around it. And that's essentially to reflect that there are two major resonance structures whereby you've just moved around all the double bonds. And so you might be thinking, Samantha, like, where did the carbons and hydrogens go? We'll be going over that, don't worry. Last thing is I want to make sure you guys know that you have to be moving all these double bonds around. So for example, let's say we want to move this double bond between carbons 2 and 3, just down by 1, but we didn't move anyone else. What would happen there? So I'm going to draw him one more time. Oop, not there. Imagine you have all these hydrogens around too. I will draw them real quick. And so some of you are hopefully seeing that there's already a kind of a major problem here with this carbon, carbon number 4. He now has 2, 4, 6, 8, 10 electrons around him. That is breaking the octet rule. That's why something like this would not be a resonance structure. Make sense to everyone? Cool. On to the next one. So I'm gonna look at this structure. Once again, find that double bond. Let's go ahead and try to, let's use yellow. Pop one of those bonds onto that oxygen what's going to happen there? Methyl group, carbon. Remember that double bond becomes a single bond. The oxygen now has an extra lone pair. I'm just going to draw the lone pairs on this guy again. Does not really matter. And so remember that you need to add your formal charges as well. Carbon is going to be plus. Oxygen is going to be minus. And so let's make sure that our overall formal charge is still the same. This guy's uncharged. This guy has a minus charge and a plus charge. Once again, for a formal charge of 0. And so there's one last thing you can do with this guy. Instead of moving the electrons from here upward onto this oxygen, you could have moved them around to mess with this guy. So one way to do that is just to take these electrons from the oxygen, pop them on that single bond with carbon, and you're going to see the following. So now carbon has lost its plus charge. The other oxygen has that plus charge now, still an overall formal charge of 0. Last example, let's do this real quick. So sometimes they won't draw the lone pairs. May help you to put them in there, so go ahead if you'd like. And so we're going to notice there are no double or triple bonds here. What else can we do? We can see these lone pairs. Go ahead and you can move them left or right. It does not matter, whatever you prefer. Let's see what happens when we try to do this. So we have a double bond with that carbon now. The rest of the molecule, if you want to draw it out. So we're going to have a plus charge here. And then you might be like, okay, minus charge here, but let's think about this carbon. It once again has how many electrons? 2, 4, 6, 8, 10. That's not going to be great. Again, breaking the octet rule, that's not going to work. You're going to see if you tried to move that lone pair over to the right instead of the left, same difference. This guy is not going to have a resonance structure. So no resonance structure. Any questions before we move on?
So like when you're creating the resonance structure, the first thing like you should look for is a double or a triple bond, and then you move it.
Yeah, perfect. I think that's a good way to do it. Essentially, you want to look for electrons, like Sydney was talking about, that you can liberate, either move away from a charge or move toward another atom. So usually where you're going to be able to find your electrons is in like a double or triple bond, creating a single or double instead. Or you can also look for a lone pair. In this case, it didn't really work just because this is a different kind of structure. But you can imagine that in, for example, this structure, we moved this lone pair over and we didn't have to use that double bond initially. Does that make sense?
Yeah.
Got it. Awesome. All right, let's move on. So just a little bit of recap for resonance. The best resonance structures are going to have a complete valence shell on every atom. So usually that's going to be a full octet. And then these next two are going to come essentially in unison. But you also want the least number of overall formal charges, or in most cases, the least separation of formal charge. So remember over here, for this middle example, this original structure has no charges. It's going to be a little bit more stable, a little bit more favorable than something like one of these that actually has charges. And so also, if you do have charged molecules, you generally want the negative charge to be on the most electronegative atom, or the positive charge to be on the least electronegative or electropositive atom. So for example, let's say we had oxygen, it's negatively charged, carbon, negatively charged. Someone go ahead and shout out or say in the chat, which one is more electronegative, oxygen or carbon?
Oxygen.
Oxygen, perfect. So you're going to want your oxygen to have the negative charge. So carbon, not as favorable, oxygen, yay. So if we looked at this one, positive charged on the least electronegative or most electropositive atom. Once again, let's do oxygen and carbon. I think you'll know that carbon is more electropositive than oxygen is going to be. So oxygen is a no, carbon is a yes. And so you might be looking at these rules and be like, oh my God, that's a lot of words. Like, what am I supposed to do with this? But essentially, as with everything in Orgo, stability is going to be key. So just think about what is going to give you your most stable molecule. What seems to make more sense? Would you rather have a O minus or a C minus? And then this will start to become intuitive. So don't worry. Cool. And a little bit more practice before we move on to the last part. Do I want to? Yeah, I'll go ahead and do this. So let's identify the major resonance structure for each of these examples. I'm going to go through this a little bit quick just so we can get through the last part. But if you have any questions, feel free to ask me after. So for the first one, these two structures, we're going to notice that the major difference is where the negative charge is. So carbon over here, or oxygen over here, who is more electronegative. Oxygen is going to be more electronegative than carbon. So we're going to say that this is the butter resonance structure. This is the minor one. So I'm going to say 1 for first place, 2 for second place. Go on to the next one. So here you're going to notice this is kind of like the one we just did earlier, a few slides earlier. So this has no charges. This has 2 charges. This has 2 charges. Major difference between these two is going to be the placement of the plus charge, nitrogen or carbon. But also notice that this carbon actually only has how many electrons? It only has 6 electrons. So that's not a full octet. So we know immediately this structure, probably not very good. I'm going to go ahead and give it third place. Remember that you prefer something without. And now on to the last one. You're going to notice the left and the middle structure are pretty similar. They're not exactly equal because remember, you can imagine these oxygens as being 2 different oxygens, but they are going to be equally major. So I'm going to say 1 and 1. You can guess that this guy has to be the minor one, but you can also look at the charges here. Remember, this is 3 charges versus 1 charge and 1 charge. Even though the overall formal charge is the same, having more charges is a little bit less stable. So I'm going to say this is 2. Remember, separation of charge is bad. Any more questions on resonance? Yeah, Noah?
So yeah, on your second example here, the central carbon had less than a full octet. So when we were drawing resonance structures, because I know we talked earlier about you can't exceed the octet except for like rare exceptions. But when we're drawing resonance, we should consider cases where we're under the octet, like we have a deficit, like those can still be valid resonance structures we have to draw.
Yeah, I definitely say under the octet is usually safe for the most part. And go ahead, Sydney, if you would like to jump in as well. For the most part, if a professor is going to ask you, they're going to ask for the major resonance structures. So they might be looking for this guy and then maybe his friend if they want one minor structure. If they were to ask for every resonance structure, I would go ahead and include things that don't have a full octet. What do you think, Sydney?
I'm sorry, can you repeat the question, Sam?
Yeah, so essentially, Noah's asking, you know how for instances we're talking about, you want to make sure you have a full octet. My thinking is if a professor asks you for every single resonance structure, you could include instances like this carbocation where you have less than an octet, but generally they're just going to ask you for major structures. I'm trying to think of an example where
I
we
would
had to put res
agree.
minor.
Like usually in my humble experience on tests, they do say major structures, or I think I've seen problems in 3570 where they're like, I don't know, circle the major structure. Like, I think that's a key. I've never seen one where you've had to draw like or worry about like every single possible structure and get points off if like you didn't include like every single like, well, at least for the major structures, yes, but not like the minor ones.
And you're
for
going to
resonance.
see, everybody, that once you get into Orgo, you're going to be dealing with more complicated molecules. So if they did ask for like every single resonance structure, that would take a while. So I think you're definitely safe putting the major ones, that's what they're going to ask for anyway. If they did want minor ones as well and didn't specify, ranking or something, I think you're perfectly fine doing this. And I definitely think you can argue that this is a resonance structure if they were to be like, oh, like this isn't what we were looking for. This is still a resonance structure. Awesome. I see another raised hand.
Hi, my
Hey.
question was on the second one as well,
Mhm.
where it says like not a full octet. So I was just wondering, like,
Sorry, I think you cut out a little on my end. I don't know if that's
Oh.
my Wi-Fi, but
sorry, I don't.
no worries.
Oh, I think it's my Wi-Fi. Is there any way you could explain like how the molecule is not following the octet rule in that one?
Yeah, so for this run, remember what is the octet rule saying essentially?
Molecules have electrons.
Yeah, it wants 8 electrons. So let me go ahead and zoom in on this guy. You see, for this carbon, it has 1, 2, 3 bonds. And so in each one of those bonds is going to be 2 electrons. Be 6 electrons instead of your 8, slightly under, so it isn't a full octet. Does that make sense?
Yeah, that makes sense. So how can this
Awesome.
even be a resonance structure though? Because it only has like 1 plus charge. So it's like, I'm just wondering, like, would that even be a resonance since it's not complete? Or
Yeah, so when we're talking about resonance structures and breaking the octet rule, I think for most instances where you have more than 8 electrons, that really can't exist as a molecule. Sydney, correct me, other Sydney, correct me if you think otherwise. But there are instances, and I know this is a little bit confusing, where if you are a little bit under the octet, that can exist, although not super stably for a little while. You're going to see a lot of reactions in organic chemistry are going to be using carbocations. And so usually this is going to function as an intermediate. You can imagine something like this molecule is going to want to shift around its electrons, so it does have a full octet everywhere. But remember, for resonance structures, it's going to be essentially like an amalgam or an average of every single resonance structure that a molecule has, and that's going to represent the molecule's actual arrangement. I know that is a little bit confusing, but remember that electrons are always zipping around everywhere. So yeah, this can still be a resonance structure, albeit it's not a very stable one. I definitely think instances where you're a little bit under the octet are more likely than when you're over the octet, because I don't think atoms can handle that many electrons. Sydney, correct me if I'm wrong.
No, I think that sounds about right. Like we see a lot of carbocations, which is again just a carbon that has a positive charge, is not meeting the octet. Usually it has 3 bonds. We see those a lot, as Samantha said, as intermediates. And I would agree that we more frequently see molecules that are below the octet versus above, especially for at least the second row atoms, just because they physically can't have that many. I mean, obviously there are exceptions for atoms such as sulfur, which are hypervalent, as Samantha said, but yeah.
Awesome. Did that answer your guys' questions? I know the octet rule is a little confusing as always, but remember, most professors are going to ask for the major resonance structures. If they ask for every single one, you can go ahead and include these guys. I don't think that's very likely that they'll ask for like every single one. So just go with the ones work out. Cool. And now I know it's a little bit past 12. I know some of you have things to do, so go ahead and leave if you would like. I will be going over drawing skeletal diagrams, so please watch the recording of this. Shouldn't be very long if you need to leave now, but I'm going to go ahead and go over this real quick. So last but not least is going to be organic molecules. So a lot of these times, like I just said, I'm going to call them skeletal drawings or some version of this. And so this is a way to draw organic molecules really quick. So just bear with me as I explain this, but essentially your lines are going to represent your different bonds. A single bond is just going to be 1 line, double bond 2, triple 3, that kind of thing. And then at each point or corner, you're going to have a carbon. Also, any hydrogens that are attached to carbons will not be drawn. So let's look at an example for this. So let's look at this molecule down here. 1, 2, 3, 4 carbons. and how many bonds are connecting those carbons. So only between the carbons, 1, 2, 3 lines. And so this is going to translate to a skeletal drawing right on the right, where you have 1, 2, 3 lines, and at the corners, 1, 2, 3, 4 carbons. So an easier way to visualize this might be something like this. Same difference as what we had before. I'm just going to draw these guys in like this. I'm going to put this on the other side. And so you might be thinking, okay, why do we even have these angles here? Why can't we just draw lines? So what if I just do it straight like that? That you might be able to get the gist of it, but if I do that really fast, just like a line like that, you might be like, Samantha, like, what the heck is that? Is that 2 carbons? Is that more? What? And so that's one reason why we're going to have these angles here. Another reason is you want to essentially remember the different hybridization schemes you're using. So for any one of these carbons, it's going to have 1, 2, 3, 4 groups. That's going to be sp3. Remember, the angle for sp3 is more or less 109.5. And so these angles are more or less 109.5. You don't have to be super exact. They're not going to take out a protractor during an exam. But yeah, that's why you have these angles here. And so the only instances where you really don't have angles between things are when you have hybridization schemes that are giving you straight lines. So for example, actually let me remove that. You look down here, there's a triple bond between these 2 carbons. Both of these carbons are going to be sp hybridized, and that's going to be 180 degrees, aka linear. That's why you're going to see something like this instead of this. This is bad. That doesn't follow the hybridization scheme. This does. Remember, there are 1, 2, 3, 4 carbons. So let's draw them in. 1, 2, 3, 4. Remember, 2 single bonds between these carbons on these sides, and then a triple bond in the middle. Any questions on that so far? I think there's a question in the chat. Oh, thank you, Jennifer. Perfect. Yeah, this is going to be the last part. Again, anyone who has to leave, feel free to just catch up on this for the Canvas site. And so last thing is just going to be some more structure drawing practice. If you think you got the hang of this, feel free to just leave, do it on your own, come back, look at the answer, really whatever you want. Let's go ahead and label these 1, 2, 3, 4. Going to go through these a little bit quick, so feel free to let me know if this is a little too fast. Remember, look at your carbons, 1, 2, 3, 4 carbons. Hydroxyl group is OH at the end. Remember, like we said before, at each point you're going to have a carbon. You're not actually going to write in the word C unless you just want to visualize it a little better. And so for anything that is not a carbon or a hydrogen attached to a carbon, you will actually write it out. So remember, 3 bonds, 1, 2, 3. You have a carbon here, 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 here. And then remember, you're actually going to have a hydroxyl as well. So I'm going to get rid of those carbons and draw this hydroxyl. Remember, you want to draw that H because it's not attached to a carbon, it is attached to an oxygen. Still, 1, 2, 3, 4 carbons, and then all the hydrogens attached. Let's go on to the next one, this guy. So look at your carbons again, 4 of them. And then there's going to be this NH group. You want to draw that. Oh, my bad. There we go. Lone pairs if you'd like. Doesn't really matter as long as you have the correct charge. Remember, 1, 2, 3, 4 carbons. Want to draw out both the N and the H. Let's go to number 3. You have 4 carbons, 1 hydroxyl group. Gonna look a little bit like the above, except remember that the branching here is a little bit different. Let's count our carbons at the end to make sure we got the right amount. 1, 2, 3, 4. 1, 2, 3, 4. Last but not least, this guy. Remember, the only non-carbon here is this double bond to an oxygen. You want to draw that as 2 lines to reflect the fact that it's a double bond. And here we go. Another way to draw this is something like this. And so you're going to notice that this hydrogen, it actually is attached to a carbon. Sometimes you will see professors drawing in the hydrogens, even if they're attached to carbons. Usually this is when you're doing a reaction and they want to show, a removal of a hydrogen or some kind of shifting of groups. But this is the correct skeletal structure. Generally, if you see something like this isn't incorrect, but usually you're going to see this more when you're dealing with the reaction that's either moving one of these guys or removing him. Does that make sense to everyone? Cool. That is the end of this lecture. Thank you for those who were able to stay over. As always, this will be posted on the Canvas and on the YouTube, so you will have more than enough chances to look all this material. Yeah, that is all I have for you.
Thank you.